Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In last few lectures we have been discussing the rotational spectroscopy and vibrational spectroscopy of both diatomic and polyatomic molecules. We saw that to carry out rotational spectroscopy we used microwave radiation, because that radiation had just about enough energy to excite the molecules in their rotational energy levels. In other words, these radiations could change the rotational motion of the molecules, thereby changing their dipole moment, and the changed dipole moment of the molecule now interacts with the electromagnetic radiation's dipole moment, such that the spectroscopy or the transition occurs and then the spectroscopy is successful. Similarly, in case of vibrational spectroscopy, we realized that it takes greater amount of energy to vibrate the molecule than it takes than what it takes for the molecule to rotate. So, therefore, to do vibrational spectroscopy we used higher energy radiation, that was infrared radiation. By shining infrared radiation on the molecule, we started vibrating the molecule, and once the molecule vibrates, in certain ways of vibration the molecule changes its dipole moment. By this, when the dipole moment of the molecule changes, now the molecule starts interacting with the radiation and we see the transition and the spectroscopy is again successful. Now, while microwave radiation does not have enough energy to vibrate the molecule, the infrared radiation has enough energy to vibrate the molecule, but simultaneously it has also enough energy to rotate the molecule. So, therefore, when we are using infrared radiation, we are not only vibrating the molecule, or we are not only changing the vibrational motion of the molecule, we are also simultaneously changing the rotational motion of the molecule. So, therefore, when we are using infrared radiation, both vibrational and rotational motions are simultaneously changed. So, therefore, we have a new spectroscopy where we can see both rotational and vibrational structures. This spectroscopy is called rho vibrational spectroscopy, rho from rotational and vibrational vibrational spectroscopy. So, together we call it rho vibrational spectroscopy, and this is the topic of our discussion today. We will look at the rho vibrational spectroscopy. As I told you that now our energy levels are not only vibrational energy levels, but they also have their rotational identity. So, instead of writing E v for vibrational level or E j for the rotational level, I am defining two indices E v j, because now the energy levels that I am discussing have both vibrational identity as well as rotational identity. So, E v j, the energy of a rho vibrational energy level, can be given as. So, first let us consider the vibrational contribution. So, we know the vibrational contribution is h bar omega v plus half. So, here we are considering a one dimensional case. So, that our discussion is easy, but it is straightforward to extend this discussion to multidimensional harmonic oscillator problem. So, we have the vibrational energy level. This is a harmonic approximation, but we also know that we can have anharmonic correction to this energy levels. These anharmonic corrections were given by h bar omega chi e, where the chi is at the unharmonicity. So, this value of chi e, which if it is 0, then this problem is purely harmonic, and for larger value unharmonicity is greater. So, this is the vibrational energy level with anharmonic correction. If you remember, we also have the rotational energy levels that we gave as b into j, b j into j plus 1, where j is the rotational quantum number. Now, in addition to this rotational energy, we also discussed that when the molecule starts rotating faster, so it undergoes a centrifugal distortion, and that also can change the rotational energy level. So, to take into account that, we had this centrifugal distortion correction. So, now this is the energy level of a rho vibrational state with anharmonic correction as well as centrifugal distortion correction. Now, we are going to discuss about both vibrational and rotational level. So, we know that rotational energy levels are very closely spaced as compared to the vibrational energy levels. So, therefore, in most of the cases the anharmonic correction that we have here are going to be small, although they are not necessarily always going to be smaller than the rotational rotational energy levels, but most of the cases they are going to be much smaller. So, therefore, we can ignore the anharmonic correction. Coming to the centrifugal distortion correction, there is no two way about it that this centrifugal distortion is extremely small. So, therefore, from our discussion we can now for the time being we can ignore these two correction terms. So, therefore, we have under the harmonic and rigid rotor approximation, the energy levels are given by this, where V is the vibrational energy level, J is the rotational energy level. So, this is the rho vibrational energy level that we have. Now, one more thing that you must remember, if you recall our discussion on B, the rotational constant, from using the spectroscopic value of B, which we obtained by looking at the line spacing in a rotational spectrum, we use this B to obtain molecular information about molecular structure. For diatomic molecule, we use B to obtain bond distance. Of course, now you can imagine that if I have started vibrating my molecule, if I am going to a vibrationally excited molecule, where the molecule exists at an excited vibrational level. So, in that case, of course, the bond distance is going to be different compared to this equilibrium bond distance. And in that situation, of course, I am going to expect the rotational constant would be different from one vibrational level to another vibrational level, because at different vibrational levels the molecular geometry changes. So, therefore, the rotational constants are also going to change. So, therefore, B should ideally be written as BV, so that it can be B0, which is the rotational constant when V equals 0, that means for the ground vibrational state, or B1 the rotational constant for the V equals 1 level, or B2 or B3 or so on and so forth. But for our discussion, just to make the analysis little simple, we would make this, we will ignore this vibrational state correction to the rotational constant, and we simply call it as B, the way we are defining here right now. This picture tells us the vibrational rho vibrational level. The blue line indicates the ground, the vibrational state, V equals 0. So, and this is V equals 1. Not only the blue line has V equals 0, this also has J equals 0, because this is the ground rho vibrational state, and we know when J equals 0, there is the rotational energy is 0. So, therefore, it is just coinciding with V equals 0. Similarly, this level also has J equals 0. Now, you would see that the next line that we have here, this corresponds to J equals 1, J equals 2, J equals 3, and similarly here J equals 1, 2, J equals 3, J equals 4. Just to distinguish our J, let us give double prime to the lower rho vibrational state and single prime to the upper rho vibrational state. So, these are now our vibrational energy states. What are their energies? When V equals V0, J equals 0, of course, the energy is purely coming from the vibrational energy, which is h bar omega into V plus half. So, which is nothing but half h bar omega, and V equals 1, the ground energy will be 3 half h bar omega. Now, of course, J equals 0, it does not contribute anything to energy. When I have J equals 1, the energy gets added up. So, if you calculate this energy when J equals 1, I have 1 into 2, so 2B. So, this ground vibrational energy plus 2B, and for this state ground vibrational energy plus 6B, ground vibrational energy plus 12B, and so on. Similarly, for the upper vibrational upper row vibrational states, we have the ground state is 3 half h bar omega. The first row vibrational state in the upper vibrational level is 3 half h bar omega plus 2B, and the second one is 3 half h bar omega plus 6B, the third one is plus 12B, and so on and so forth. So, these are the energy levels now. Now, starting from the lower vibrational level, we can induce transition to the upper vibrational level using infrared radiation. So, we know pure vibrational spectroscopy is obtained when we go from V equals 0 to V equals 1. In both cases, rotational levels are not excited. That will be pure vibrational, but as I said, when you use infrared radiation, the radiation window is broad enough to carry out when it goes from V equals 0 to V equals 1, it can also take the molecule to a different rotational state. In addition to that, we also know that rotational energy levels are very closely spaced. So, therefore, at room temperature J equals 0, J equals 1, J equals 2, most of the cases these lower J values are already populated. In fact, larger J values have greater population. We already have discussed about how the population increases as with increasing J up to a point, and then it comes down. So, we know that higher levels of J's are also populated. So, therefore, when we look at the row vibrational transition, we have to consider the transition not only from V equals 0, J equals 0, but also from V equals 0, J equals 1 to higher levels. So, let us see what all we can do here. Now, you can see the lower energy level, row vibrational levels have J double prime is 0, 1, 2, and higher one are have similar energy. Starting from J double prime 0, starting from this level, I can only go. So, since just to recall the selection rule here. So, we have infrared selection rule is delta V equals plus minus 1, and the rotational is delta J equals plus minus 1, and also delta J equals 0, but for diatomic molecules this is delta J equals 0 is not there. Now, suppose we are considering absorption the way we are discussing here, only going from lower vibrational level to upper vibrational level. So, therefore, delta V is only plus 1 because it will goes from V equals 0 to V equals 1. But while we are discussing absorption spectra, we can have delta J as plus 1 or delta J as minus 1. How can we have delta J as plus 1? If I start from J equals 0 and reach here J equals 1, that will be delta J as plus 1. Can I do delta J equals minus 1 from J equals 0 level? No, because J is 0 here. So, the lowest energy J value is also 0 in the upper state. So, therefore, delta J minus 1 is not allowed when I start from J equals 0 level. But when I start from J double prime as 1, I can either go J double prime 2, that is a delta J equals plus transition, or when I look at J double prime 1 and I can go to J prime of 0. In this case, the left line, the left transition is delta J equals minus 1, the right transition is delta J equals plus 1. So, from J double prime 0, I can show a plus 1 transition, delta J equals plus 1 transition, where it goes from 0 to 1 level, and similarly starting from 2, I can go to 3, starting from 3, I can go to 4. These are all delta J equals plus 1 transitions. And if I start from J double prime equals 2, I can go to J double prime equals 1, which is a delta J equals minus 1 transition. So, J double prime 3 to J double prime 2, again a minus delta J equals minus 1 transition, and 4 to 3, and this is delta J equals minus 1 transition. So, we see that there are some transitions which are delta J equals minus 1, some transitions which are called delta J equals plus 1 transition. So, delta J minus 1 transitions are called P lines, delta J plus 1 transitions are called R lines. Let us consider first the case of delta j equals minus 1. So, that means it goes to from a higher value of j to a lower value of j, and try to find out what is the energy difference when it undergoes delta j equals minus 1 transition. The energy difference is what we are trying to find. So, let us say that we are going from j to j minus 1. So, this is j double prime, this is j prime, initial state, final state. The energy of this initial state is half h bar omega plus b j into j plus 1. The energy of the final state is 3 half h bar omega, that is because we are going to upper vibrational level, plus b j minus 1 into j, because we have this formula of j into j plus 1, but this j is now j minus 1. So, therefore, j minus 1 into j. Now, the delta E, if you obtain this and the right hand energy minus the left hand energy. So, this energy will be h bar omega minus 2 b j, where j is the rotational contour number of the lowest level or j prime level. So, therefore, let us find out what is the, when I go from j equals 0 to minus 1, of course, that is not allowed. So, the first one that will be allowed is j equals 1 to 0, and in this case delta E would be h bar omega minus 2 b, because that is j equals 1. So, or I can go from 2 to 1, in that case delta E would be h bar omega minus 4 b, and you would see that when I go from 3 to 2, delta E would be h bar omega minus 6 b, and so on and so forth. So, we get for delta j equals minus 1 transitions, we get this kind of lines. So, this transition when it goes from j equals 1 to j equals 0, as I already said that delta j are called p lines. So, this particular line is called p1 line, because it starts, it is a delta j equals minus 1 transition and its initial j value is 1. So, therefore, it is p1, and this line is called p2 because its initial j value is 2 and it is a delta j equals minus 1 transition, and this is called p3 line, and so on and so forth. Now, this is about delta j equals minus 1 discussion. Let us consider now delta j equals plus 1. When I have delta j equals plus 1, so that means I am going from energy level j to j plus 1. So, this is j double prime, this is j prime, initial state is j, final state is j plus 1, but you remember that we are talking about the final state is the rho vibrational state of the upper vibrational level. So, therefore, let us find out the energy. The energy is half h bar omega plus b j into j plus 1 of the initial state, and the final state's energy will be of course 3 half h bar omega, because that is the upper vibrational level, plus b j plus 1 into j plus 2. Again, because the energy expression is b j into j plus 1, but our energy, rotational level is j plus 1. So, therefore, this is the energy. When we calculate the delta E, you would find that this delta E would come out to be h bar omega plus 2 b j plus 1. When you take the difference of this energy level and this energy level, you would get this delta E. Now, let us see for a few transitions. Suppose we start from j equals 0 to j equals 1, that transition will have delta E of h bar omega plus 2 b, because j is 0. So, therefore, the j plus 1 is 1, and 1 to 2 transition delta E would be h bar omega plus 4 b, 2 to 3 transition will be delta E equals h bar omega plus 6 b, and so on and so forth. So, we see that we are having we can have a general expression for delta j equals plus 1 and delta j equals minus 1 transition. Similarly, the way we define gave names to this delta j equals minus 1 lines, we can also give similar names to the delta j equals plus transitions. For example, as I said, delta j equals plus 1 transition is named by as R transition. So, therefore, the first line that we see from j equals 0 to 1, we can call it R 0 because it involves delta j equals plus 1, that is why R, and initial level is 0, that is why R 0, and this one will be R 1 and this is R 2 and so on and so forth. When we look, if we translate this to a spectrum, suppose I have this energy axis and this is my h bar omega. I draw some grid where the separation of each point is 2b. So, this one is h bar omega, this is h bar omega plus 2b, this is h bar omega plus 4b plus 6b, this is h bar omega minus 2b minus 4b and so on and so forth. So, let us see where these lines are appearing. Suppose P1 line would appear at h bar omega minus 2b. So, I draw this P1, P2 line would appear h bar omega minus 4b, P3 would appear h bar omega minus 6b and so on and so forth. The way as you know, the intensity of these levels would actually depend on the J values and the temperature. So, we typically see a shape of the population distribution as is shown here. Now, let us look at the R lines. The R lines, the first R line appears at h bar omega plus 2b, this is h bar omega. So, the first R line h bar omega 2b, R 1 appears at h bar omega 4b, h bar omega plus 6b. So, to give these names, so this is P1, P2, P3, P4, this line is R 0, R 1, R 2, R 3 and so on and so forth. So, you see what we have here, we have first line to the left of h bar omega P1, the first line right to the h bar omega is R 0, and this energy difference between P1 and R 0, this energy difference is called zero gap. So, in a typical rho vibrational spectrum, you would see the vibration at the center, at the central region of the rho vibrational spectrum, you have some gap, and that gap is called zero gap, and we see how this zero gap is coming. Now, if we convolute this both P and R side, you would see that there are two distinct features separated from each other by this zero gap. So, this side is called P band, this side is called R band. One important feature is that when we in this discussion what we have done is that we have only considered delta j equals minus 1 and delta j equals plus 1, but we know that in some polyatomic molecules we would also start seeing delta j equals 0 transition. When we have delta j equals 0 transition, what would happen is that when I start from lower value of j equals 0, I go to upper value of j equals 0. So, therefore, the rotational correction that I am getting will cancel out from the upper vibrational level and lower vibrational level. So, therefore, no matter from which level rho vibrational level I am starting, if delta j equals 0, the only transition that will appear would appear at h bar omega. So, just to continue our discussion, so I just would like to fit everything in this, so that we have everything right in front of our eyes. Delta j equals 0 transition. So, we have j double prime equals to j prime. So, therefore, delta E would be always h bar omega, no matter what is j, what is the initial value of j. So, therefore, from j equals 0 to j equals 0 or j double prime 0 to j prime 0 or j double prime 1 to j double prime 1, they will appear at h bar omega. And these lines, when delta j equals 0 lines are there, they are called Q band. So, that we have P, Q and R. So, just to draw some delta j equals 0, I have j 0 to 0, this is 1 to 1, 2 to 2 and so on and so forth. So, these are R lines, these are P lines, these are Q lines. Now, if I draw these Q lines in this spectrum, you would see that all these transitions j equals 0 to j equals 0 or 1 to 1, 2 to 2, all these transitions will occur at the same energy. And that would appear at h bar omega. So, to draw this line, I am just putting a very high intense line over here. So, which is for the Q band. Mind you, there is no as such we do not distinguish now for Q0, Q1, because all of them are going to appear at one energy level. And when we make this profile often looks like this. This is a typical shape of a rho vibrational spectrum where delta j equals 0 transition is allowed, and this region where Q band appears, this is called band head. And this band head is very easy to identify in a spectrum, because this is the high energy, high intensity region. And if there is no Q band, then we see a clear 0 gap, which is the energy difference between the P lines and the R lines. The discussion that we had, of course, we made some assumptions. For example, we ignored the unharmonicity. We also ignored the fact that rotational constants are going to be different for different vibrational levels. So, these simple expressions that we obtained them because the B value, rotational constant at V equals 1, and B value, the rotational constant at V equals 0, both were identical. But we know they are not going to be that is not going to be the case in a real system. So, therefore, B in the upper vibrational levels, when you have B prime and the lower vibrational level, we call it B. So, if there is a difference in these rotational constants, of course, there will be slight change in these energy levels, and not only that, you would start getting delta j equals 0 transition. That means, the Q lines at different energy levels, because now B prime and B are different. But as long as we assume B prime and B are same, the Q branch would Q lines would all appear at the same energy h bar omega. So, in this class we discussed about the rho vibrational spectroscopy, and rho vibrational spectroscopy comes into picture because when you use infrared radiation, we not only excite the molecule in its vibrational state, we simultaneously excite the molecule in their rotational state. So, therefore, in often cases both rotational and vibrational motions are changing because of infrared radiation, and the corresponding spectrum that we get, we call that rho vibrational spectrum. Thank you for your attention.